Welcome to the section 1 of lecture 7. In this video, we will introduce how to invert Laplace domain expressions with repeated roots using the partial fraction expansion technique. In lecture 6 videos, we talked about inverting Laplace domain expression that have either had real distinct root or had complex roots. This time, the expression will have repeated roots, which is case 3 in partial fraction expansion in the course packet. When we say that the Laplace domain expression has repeated roots, we mean that the denominator can be written as a series of expressions that have repeated s plus p terms from 0 to n powers. With repeated roots, the partial fraction expansion will be written as a series of ratios with a coefficients as the numerators and denominators that have repeated s plus p terms with increasing powers as shown here. Here is an example Laplace domain expression, 1 over s times s plus 1 cubed. This is part of example 6.5 in the course packet. We are going to solve this by hand. Later, we will solve it using MATLAB. From this expression, we can see that we have repeated roots because the terms s plus 1 is cubed. Be advised that the denominator can be written in other forms where it may not be clear from the beginning that the denominator has repeated roots. But in this case, we know that we will have repeated roots. Knowing this, we can write the partial fraction expansion using all of the repeated roots and the root of 0. So we can get an expression of a over s, which is the expression when we have a 0 root. Then we write the repeated roots terms, b over s plus 1 cubed, c over s plus 1 squared, and d over s plus 1. We don't know a, b, c, d, and we need to find them. To find a, we do what we have done before following the procedure on page 6-5 of the course packet. We multiply both sides by s, simplify, and then set s equals 0, and solve the expression for a. We will find that a equals 1. To find b, we multiply both sides of the expression by s plus 1 cubed. Simplify and then set s equals minus 1. After solving for b, we find that b equals minus 1. Now we know a and b. Next, we need to find c and d. We start by substituting in the known values for a and b. Then, we put terms over a common denominator, which is the same as the denominator on the expression on the left side of the equal sign, which is s times s plus 1 cubed. We do this by multiplying the first term on the right side of the equal sign by s plus 1 cubed over s plus 1 cubed. Then the next term is multiplied by s over s. The next multiplied by s times s plus 1 over s times s plus 1. And then the last term multiplied by s times s plus 1 squared over s times s plus 1 squared. Note that we are multiplying 1 to each term because the numerator and denominators are the same. After all of the terms have the same denominator, we combine the numerator terms on the right side of the equation and then we equate the numerators. Expand the numerator on the right side and combine like terms, and set it equal to the numerator on the left side of the equation. After doing that, we get the equation shown here. The equation gives us 3 expressions for finding d and c. We know that all of the s terms have to go away, so s plus 1 plus d must equal 0, and 3 plus c plus 2 times d must equal 0, and 2 plus c plus d must equal 0. And we can see that d must equal minus 1 and c must equal minus 1 too. Then we can write the partial fraction expansion using a, b, c, d. And this produces the following equation, which is xs equals 1 over s minus 1 over s plus 1 cubed minus 1 over s plus 1 squared minus 1 over s plus 1. These terms we can invert using equations 5, 18, 16, and 15. We find that the time domain solution xt is equal to 1 over t squared over 2 times e to the power minus t, minus t times e to the power minus t minus e to the power minus t. Okay, let's solve the problem again using MATLAB and the residue command. Here is the residue function. The MATLAB residue function returns a1 equals a2 equals a3 equals minus 1, and a4 equals 1. R1 equals R2 equals R3 equals minus 1, and R4 equals 0. The fact is that R1, R2, and R3 are equal minus 1, which means that we have repeated roots. To write the partial fraction with repeated roots, we need to know that the MATLAB assumes that the powers of repeated roots terms increase from 1 to 3, or as many repeated roots you have. So you have to follow the order, increasing from 1 to n. So this means that the partial fraction expansion of xs is 1 over s plus 1 minus 1 over s plus 1 squared minus 1 over s plus 1 cubed plus 1 over s. The last term is because of the zero root for R4. Repeated roots do not always have minus 1 as the numerators, as this example shows. The expression can be inverted using equations 15, 16, 18, and 5 to get the time domain result shown. This was the same result found before. The final and fourth case, which we've used multiple times, is simply recognizing the function in column 3 of the Laplace transform table. The example here illustrates that 25 equals 5 squared. When we make the change, the equation can be found to be equation 29 in the table. This concludes the video for Lecture 7, Section 1, and the information on how to invert Laplace domain equations. We have covered how to invert Laplace domain expressions with real roots, complex roots, and repeated roots. Please write down any questions you might have and bring them up in class. Thank you.